Okay, so good afternoon, and this is our video lesson on the first part of chapter 3, which talks about the extrema on any function on a closed interval. Okay, and so I want to kind of go through the notes. Please follow along, in the back of your packet, kind of go through this, and obviously feel free to pause the video, solve the problems, come back, rewind, things like that. And that way, you're actively, taking notes as if you were, in class. And so the first thing I want to talk about on this is what it means to be a critical number. Okay? And I'm going to talk about critical values, or sometimes I like to call them suspicious values, things that we should be paying attention to very closely. And for right now, if we link critical values or critical numbers in the language of calculus, critical numbers are going to be what I'm going to call anytime there are undefined derivatives or zero derivatives. So critical numbers are any, I'll call them like x values with a zero or undefined derivative. Undefined derivative. Okay, so, and it is the x value. I'm interested in when is it happening. And so it's any x value with a zero or undefined derivative. That's like the worst looking word of derivative I've ever seen. Derivative, okay. Okay, so then, so that's kind of like getting us through the lens of calculus. Okay, these critical numbers, any point where the derivative is zero, undefined. It might be undefined because it's not in the domain, or there's a cusp, or there's a vertical tangent line, but we're going to call those critical values, okay? And then to kind of link that to this idea of extrema, and extrema just being the plural for the highs and the lows, the maximums and the minimums. Okay, so a function, if your function is continuous, right, and it's on a closed interval, okay, and those two descriptors are going to be so important, and we're going to see at the end of the lesson what happens if you take one or both of them away. But if you are continuous on a closed interval, call it a to b, then your extrema, right, your maximums or your minimums, together collectively, then your extrema are in fact those critical values. Okay, then the extrema will be the critical values. Okay, and so those critical values, now we're going to start associating at least their x value. Remember, those are the x values. Okay, it's not necessarily the maximum value, which is a y. It's not the minimum value of that function, which is a y. But when it's happening, it's the x. Remember, that's the when. When is it happening? Those x values, those would be the critical values as long as you're continuous on the closed interval. Okay, so a couple of just some algebra examples that we want to work through. And again, feel free to pause the video. You do the problem and then play the video, and kind of see the answer if you want. It's up to you, or follow along the first one. It's fine. Okay. So let's see. Find the extrema of this function on this interval. So again, it's closed interval, and this is just a polynomial function, so I know it is continuous. So the extrema, the highs and the lows, the maximums and the minimums, will be the critical values. What does that mean? Well, find a derivative, find where it's zero or undefined, and then group up those x's, because those will be those extrema. Those will be the critical values. So let's first find the derivative. So f prime is equal to what? 12x cubed minus 12x squared. Okay. Now, this this derivative is also polynomial. So there's no time where this is undefined. Right? Remember, critical values are where its derivative is zero or undefined. You might get a derivative, but based on a quotient or a product or just the nature of the function, where you might have a denominator that we would be undefined in. In this case, it's not. So then I can set it equal to 0. And might as well factor 12x squared out. That would give you an x minus 1. And so I want to analyze, when is this equal to 0? This is equal to 0 when x is 0, when x is 1. The other thing I want to consider, though, is that even though the function itself, as a derivative, has no undefined values, there are actually two times where the derivative is undefined. And the two times happen to appear at the endpoints. Because when you graph from -1 to 2, you have endpoints that kind of teeter-totter, right? There's not one definite derivative. So those endpoints technically don't have a defined derivative. I mean, you take any graph, whatever it looks like, at the endpoint, there's a lot of different, places you could put that tangent line. So after you've kind of done the algebra, after you've figured out what x's are zero derivatives, you have to also include your endpoints. Your endpoints of -1 and 2, even though they're not zero derivatives, they're still critical because technically they're undefined. So I'm going to write, I want you to think about this. Don't forget this. Don't forget endpoints, because your endpoints will always be critical because by definition those endpoints will have no derivative defined. Okay, so I have 4 values that are critical values. That means the maximums and the minimums of this function would have to come at one of these 4 spots, or there might be multiple. There might be global maximums or absolute maximums, but then there also might be relative or local maximums. Same thing with the minimums. Overall, absolute minimum, or it could be like a global or a relative or simply a local minimum. Okay, how do you tell? Then you start evaluating, right? So these are the 4 values I need to evaluate in my given function. So x and f of x. Okay. And so if I think about, -1, 0, 1, and 2. And I just evaluate. So you put in -1, 0, 1, and 2. Yay, 0. 0, 0, so that's 0. Okay. Let's see, -1 to the 4th power is +1, so we have a 3. Minus 4 times that -1, that looks like 7. Okay. If I put in a +1, the only difference, literally difference, is that that's going to be a negative. So 3 minus 4 to get -1. And then 2, that's fun. 2 to the 4th is 16. 3 times 16 is 48. Minus 2 cubed is 8. 4 times 8 is 32. So what is that, 16? Okay? So if I'm looking for absolutes, it's just comparison. The absolute maximum is 16, right? So the absolute maximum is 16, and the absolute minimum is -1. Okay? If it says, when did it happen, that's when you're going to say, it's the x value. The maximum happened when x was 2. The absolute minimum happened when x was 1. And so if you take a look, 2, that was one of our endpoints. 1 happened to be one of the spots where the derivative was 0. Now, what is happening at 7 and what is happening at 0? We might need a little bit further investigation. It could be just a relative max or relative min, or it could be a false positive. And for example, what does that mean? A false positive, you might have a function that looks like this. Okay? You might get a function that has a horizontal tangent line right there, has a derivative that's equal to 0, but it's kind of part of a cube function, right? Where that's not a max or a minimum. Okay, that has actually a special name. It's going to be called a saddle point. But its derivative is equal to 0. But it's a false positive because it's neither a max or a min. And we're going to talk about these. These are still critical values. These are still points of interest. But in terms of what you might be doing for tonight's homework, really what I want you to think about is, list all of the critical values, list out their y values, and sort of identify which one's the absolute max and which one's the absolute min by just comparing. Okay, excellent. So let's see, let's do example 2. And I'll kind of walk through this one as well. Again, find the extrema. So as long as you're a closed interval and a continuous function, your extrema will in fact be the times where the derivative is either 0 or is undefined. Okay, so we definitely have a closed interval, and we are definitely continuous because x squared plus 1 over the real numbers is always positive, right? So we don't have any domain issues, right? You don't have to worry about dividing by 0. Okay, so let's take the derivative. Kosher rule, you could do power, well actually not power rule, you could do product rule. Oh yeah, you could do a power rule. You could think about it as the quantity x squared plus 1 to the negative 1. But let's just use quotient rule. Let's find low d high. So low x squared plus 1 d high of 0 minus high, which is 3, d low, 2x, all over low. X squared plus 1 squared. Well, the top cleans up very nicely. We get a negative 6x. So my derivative, f prime of x, is equal to negative 6x over x squared plus 1 squared. Okay? Now again, we have a denominator, but it's never negative. It's never 0. So there's no undefined derivatives from the function itself. When is this equal to 0? Well, by simply multiplying that denominator across, it simplifies our function quite nicely. To multiply that across, 0 equals negative 6x. So one of my critical values is 0. X equals 0 is a critical value. Okay, and so that's one of them. X equals 0, divide out the negative 6, right? Now, there are no undefined derivatives here, but we do have two endpoints. Those are always critical on our closed interval, negative 2 and 2. And so to get the y values corresponding to these, you put in 0. 0 squared is 0 plus 1 is 1, so we get an output of 3. Negative 2 squared is 4. 4 plus 1 is 5, so we get 3/5. And because that's an even function, we're going to get 3/5 as well. So here, my absolute maximum is 3. When did it happen? 0. And again, the maximum and minimum value, those are what the value is. That is what the extrema is. When did it happen? Would have been the x values. So that's our max, and we have a dual absolute minimum 3/5 on each side. And if you were to graph this, this actually is an even function, symmetrical about the y-axis. So if my interval splits that exactly in half, then that should make sense for there. Okay, so what I'd like maybe to do is take a look maybe at example 3 and 4 and 5, while and maybe work out those. And then in the next video, I'll work through those solutions in terms of seeing if you got the right answers or not.